This equation is conservation of mass for a flowing fluid, the continuity equation. It looks compact, almost like something you'd have to memorize. You don't. By the end of these few minutes, you'll build it yourself from one small box of fluid and some careful bookkeeping, with not a single step skipped. Let me erase it and let's derive it from scratch. Start with the only idea we actually need. Mass is never created or destroyed. Now draw a small box fixed in space. It doesn't move, it doesn't change size. Fluid streams through it freely. Because mass is conserved, the accounting is exact. If the mass inside the box goes up, that mass had to flow in through the walls. If it drops, mass flowed out. Accumulation inside equals net flow in. That one sentence is the whole physics. The rest is turning it into symbols. We'll track two things: the density, rho, mass per unit volume, which can change with position and time, and the velocity, with components u, v, and w along the three axes. First question: how much mass is in the box right now? Density is mass per volume, so multiply. The mass is rho times the box's volume, the product of its three side lengths. Call that small volume dv, a fixed little number. How fast is that mass changing? The box is rigid, its volume can't change, so the only thing that can vary is the density. The rate of change of mass inside is the time derivative of rho times dv. That's the left side of our balance. Next, the flow across the walls. We need the right quantity for mass crossing a surface, and that's the mass flux, density times velocity, rho u. Don't take that on faith, check the units. Density is mass per volume, velocity is length per time. Multiply, the lengths cancel down to mass per area per time. So rho u is the mass crossing 1 unit of area each second, times a face's actual area. It's the mass per second pouring through that face. Let's only look at flow along x for now, the two faces perpendicular to the x-axis. Fluid enters through the left face and leaves through the right face. The mass entering per second is the flux at the left face times the face area, which is di times dz. The mass leaving is the flux at the right face times that same area. The net loss along x is out minus in. Here is the step almost every derivation rushes, and it's the heart of the whole thing. The flux on the left face and the flux on the right face are not equal. The faces sit a small distance apart, and the flux varies smoothly through space. So write the right face flux in terms of the left value, plus the rate at which the flux changes along x, times the small gap between the faces. That's just the definition of a derivative, rearranged, the first term of a Taylor expansion. For a box this small, it's exact. Now subtract. Net mass leaving along x is the right flux minus the left flux, all times the face area. The two base flux values are identical, so they cancel cleanly. What survives is the rate of change of rho u along x, times the gap times the face area. But the gap times the face area is just the box's volume, dv. So the net outflow along x is the derivative of rho u with respect to x times dv. Nothing in that argument cared that we picked x. Run the identical reasoning for the pair of faces facing y, and again for the pair facing z. Add the three contributions, and that sum, the three derivatives together, is exactly the divergence of rho times the velocity times dv. Time to balance the books. The mass accumulating inside equals the net mass flowing in, which is minus the net flowing out. So the time derivative of rho times dv equals minus the divergence of rho u times dv. Look at both sides. Every term carries the same factor of dv. Divided out, what remains is the time derivative of rho plus the divergence of rho times velocity equals 0. That is the continuity equation, built entirely from a box and bookkeeping. Two quick payoffs. First, expand that divergence with the product rule, and you get the material derivative form, the rate of change of rho following a moving fluid element plus rho times the divergence of the velocity equal to 0. The same equation from the parcel's point of view. Second, the special case everyone uses. If the fluid is incompressible, the density is constant, both density terms drop, and you're left with the divergence of the velocity equals 0. That clean little statement is just conservation of mass at constant density. So there's nothing to memorize. Conservation of mass is bookkeeping on a box. What builds up inside is what flows in across the faces. Write the mass, expand the fluxes with one Taylor step, divide by the volume. Do those, and you can reproduce the continuity equation anytime. That's all for this video. Tell me what you want to see next in the comments.